the general formula of a sequence. We're not going to get into the limit or any of that kind of stuff. So, okay, so first of all, as far as the language goes on a sequence generally we write that like a sub n. N is just a whole number. Okay, so n is just some sort of a whole number, and like that, 1, 2, 3, and so forth like that. Okay, now sequences basically are going to have different types of terms to them, and they're usually represented by some sort of a formula. We can generally write this formula in two ways: a recurrence relation and an explicit formula. So what I want to try to get you comfortable with today is just kind of what a sequence looks like and how to build a sequence and how to write a formula for them. Okay, the hardest part of this for most students is if I give you a sequence, being able to write a formula for it. Okay, and you got to find patterns on that and everything. Okay, so basically a sequence is some sort of a function that's going to be represented in this type of notation like that. So I'm going to start off with, generally, let's just kind of do a real simple sequence like that. And see, it's infinite. It goes on forever. There's a certain pattern. Now, the pattern on this one is easy to see. I mean, what's happening? I mean, tell me what comes after 32. 42, right? What's happening? It's getting bigger by 10. So sometimes the pattern is super easy to see. Sometimes it's not. So that one is a sequence. Now, what I want to kind of do is get you comfortable with a couple of ideas. Generally, when we do this 3 dots, we call that an ellipsis. That just means it goes on forever with that pattern. Okay, so this is an infinite sequence of numbers. All right. So what we generally do is we generally just write this like this. And what that's doing is you're going from 1 to infinity like this. So basically in this sequence in example 1, n is called the index. And generally it starts with 0 or 1. Most of the time n is going to start with 1. Okay. So in this one we would say a of 1 is equal to 2. A of 2 is the second term, so that's 12. A of 3 is the third term, so that's 22. Then A of 4 is going to be 32, like that. Now the recurrence relation, let me kind of explain how you do what a recurrence relation is and then what an explicit formula is. What you do when you do a recurrence relation is you always pretty well start by just telling me what the first term is. That's step 1 in doing a recurrence relation, is to do that. Then you're writing a formula that really gives you the next term in the sequence. So you write a sub n plus 1, okay? So what you're trying to do on this is we have a of 1 is equal to 2. When we do this a of n plus 1, if you want to go to a of 2, you're really doing this. So what you're doing is you're taking that a of 1 generally, and then you're doing something to that. So really what's happening on this, well, what's the pattern on this is it's going up by 10, right? So what you would say on this is when you're doing a recurrence relation, you always want to do the previous term, and then you do something to get the next term. Okay, so you have a sub n plus 1, then a sub n. That's the next term in the sequence. So what are we doing with this? What do you do with the 2 to make it become 12? You add 10 to it, exactly. So that recurrence relation would be written like this. And you put this together like this. Both of these statements are required. Now I want to just prove to you how the language works on that. Okay, that's how you write that out. So basically, A1 is 2, we know that. But now when you go to this second formula, you're really doing a of 1 plus 1 is equal to a of 1 plus 10, okay? And what does that do? That gives you a of 2 equals a of 1, but a of 1 is 2, and 2 plus 10 is 12. So what you're doing is you're relating that to the previous term. And I'm going to do that one more time just to kind of get you comfortable with the notation. So now we go to a of 2 plus 1, which is ultimately going to give you a of 3, right? Well, according to the recurrence relation, you do a of 2, and then you do plus 10, like that, okay? Well, what's a of 2? A of 2 is 12, so 12 plus 10 is 22, and so forth. So what you're doing with a recurrence relation is you're relating, to get the next term, you're doing something to the previous term. Does that make sense? Okay? Does that, the way I'm working that out, make sense to everybody? Okay? If you went to the next one, you don't have to write this down. I just want to make sure you know the language. If you do a of 3 plus 1, of course, that's going to give you a of 4. What are you doing? You're doing a of 3 plus 10. So you're always doing the previous term and adding 10 to it. So a of 3 is 22. 22 plus 10 is 32. That's how you generate. A recurrence relation is a way of writing a formula. Okay? And you have to list the first term, and then you have to have a formula that gets the next term. Okay, now that's different than an explicit formula. Does that make sense? Does the notation make sense? Because this is something a lot of times brand new to students. You maybe have seen some sequences before, but not really written out in a specific way. Okay, now we're going to do the explicit formula. Sometimes the explicit formula is harder, sometimes it's easier. Okay, so what I'm going to do on this one now is, let's just write down kind of a chart. If n is equal to 1, we get the term 2. If n is equal to 2, we got 12. If n is 3, we got, what? So we're just going up 10, so that'd be 22. And then if n is equal to 4, we're going to have 32 like that. So what you have to do is you have to look for one formula that has the letter n in it that will generate it for you regardless. See, what our goal would be on this problem is, if you wanted to know what a of 100 is, okay, if all you have is a recurrence relation, if you do a of 100, it's kind of a bummer because you got to keep adding 10 to things over and over and over again. It would be nice if we just had a formula, we plug 100 in, and boom, we got the answer. That's what our goal is, okay? So what we need to do is we need to see if we see any type of relationship that exists in this problem. So let's kind of look at this like that. And again, our goal is maybe to have that in there. So if you look at this first thing, one way to write this is you always have a plus 10 in here, always. You can always tell you have a 10 in there. That's important. So, but you also, these things are always going up. They always have a 2 in there also. So if we did this, let's see if we can kind of generate an idea here. Okay, if n is equal to 1, wouldn't we like that to really be 0? Because then that would give 2, wouldn't it? Right? 10 times 0 is 0. 0 plus 2 is 2. If we go to n equals 2, well, it would be kind of nice if that was just a 1, right? Now it's working. See, I'm finding a pattern on this. Then if I go n equals 3, it'd be nice if that was a 2. And if n was 4, it'd be nice if that's a 3. You guys see how I'm reasoning that out? You have a 10 in there always, without a doubt. Okay? But what you really have is you have a multiple of 10. And then it's always 2 bigger like that. So if we start putting this formula together, then it's going to go like this. Okay, what we're going to say on this formula is we're going to say a sub n. Okay, that's how we write that formula. And what do we have? We have 2 plus 10 times something. But what are you going to have there? You're not going to have n there. What are you going to have there?
N minus 1.
Good, n minus 1. Look at this, okay? That thing's always 1 less than that. So n minus 1 would go like that. Now, once you get a formula put together, you got to convince yourself that it's right. So the idea would be, if n was equal to 4, well, what would you have? You'd have 10 plus 10 times 4 minus 1, so that would be 2 plus 30, so that'd be 32, right? And that's what we're supposed to get, okay? So that would be how you could write the formula. So you could write your formula like this. That's your explicit formula. Or you could even multiply it out, which is what I'm going to do. That's 2 plus 10n minus 10. So that's going to be a sub n is equal to 10n minus 8. So that would be probably the best way to write that formula, and you have to kind of do that in your head. Now, if you do this, See if this makes sense to you now. So if using this, if n is equal to 1, what do you have? You have 10 times 1 minus 8. That's equal to 2 like it's supposed to, right? Okay, let's do n equals 2. Okay, that would be 10 times, and that should be, almost looks like I'm writing that as a subscript, but that's 10 times n is what that is. So you'd have 10 times 2 minus 8. Let's see, that's 20 minus 8, so that's 12, so it works, doesn't it? Okay, so that formula works. So the idea would be now if you wanted to find a of 100, then you'd just do 10 times 100 minus 8, then you'd get your answer. Okay, and that's what your goal is. So one of the things that you have to do with these problems is you got to look for patterns. I usually recommend if you're doing an explicit formula to write down n, start with 1. You could also start with 0 on this problem, but we're going to generally start with 1 and then look for a pattern. Okay, does that make any sense? Okay, so it's an implicit formula, like I have on part B, is 2 parts of it. First term and then how you get the next term. But an explicit formula, it's in terms of n, so you can easily find any term that you want to. That's the idea. All right, does that make any sense to start with? Okay, that's a sequence. Okay, so one of the things we're going to kind of focus on here today is how to work with formulas, implicit and explicit. Okay, first thing I want to do is real simple. We're going to just take a sequence and write out the first 4 terms. Okay, this is a real simple thing to do. It's just arithmetic. Okay, so this one, we have our sequence and we're starting at 1. This terminology right there is just telling you we're going from 1 to infinity. And n is a whole number, so it's going to go 1, 2, 3, 4. There's no decimals or anything. So when you do A1, and this is a explicit formula, you're just going to do 3 times 1 plus 1. Then you're going to go on to 2 and do 3 times 2 plus 1, and so forth. 3 times 3 plus 1. 3 times 4 plus 1, and so forth like that. So that's how you generate your terms. You can do the arithmetic in your head. That's 4. This is 6 plus 1, so that's 7. This is 9 plus 1, so that's 10. And that's 12 plus 1, so that's 13. Okay? And if you look at this, well, this is going up by 3, isn't it? Well, what made it go up by 3? The 3n did. Okay? So that's the idea. And the way I look at this is kind of a worthwhile thing to write down. That right there is a multiple of 3, and then that's 1 bigger. So when I look at this formula, I just think of 1 bigger than a multiple of 3. Okay, if you think about that. So you have like 3 times 1 is 3, 1 bigger than 3 is 4. 3 times 2 is 6, 1 bigger is 7. 3 times 3 is 9, 1 bigger. That's what 3n does, is it gives a multiple of 3, right? So it's kind of nice to see those little things and how that's generating that sequence, okay? That one should be pretty easy. All right, now let's go to the next one. So we're going to start with -1 to the first over 2 to the first. We're going to work that out, and we're just going to keep varying that subscript. We're going to do -1 to the second over 2 to the second, then -1 to the third over 2 to the third. We're doing powers of 2, and then -1 to the fourth over 2 to the fourth like that. And it's arithmetic is what's happening. Now, what you're doing with this is this -1 to the n, it's either going to be 1 or -1, right? So what's -1 to the first going to be? -1. And then 2 to the first is 2, so that means the first term in that sequence is -1/2. Okay? The next one, what's -1 to the second now? 1, and then 2 to the second's 4, so you have 1/4, like that. Okay, go to the next one. What's -1 to an odd power going to be? Negative, right? That's going to be -1. 2 to the third is 8. Okay, so you'd have -1 over 8 like that. Okay, then the last one, if you take -1 to an even power, you're going to have 1, and then 2 to the fourth is 16. Okay, So what you kind of have on this, if you have -1 to an odd power, you're going to get -1. -1 to the even power is going to give you +1. And that's a real important thing when you deal with sequences and series, is that causes the signs to alternate. Okay, so you'll kind of see how those things alternate. So you might want to write down this vocabulary. We call this an alternating sequence. And when you see that -1 to a power, that's what's causing that thing to alternate like that. Okay? So really all that is it's alternating in signs, and it's 1 over some power of 2. Okay, what's happening in the denominator is it's just doubling. So the next one's going to be what? It'd be -1 over 32 and so forth. Okay? So that's what you're doing, is learning how to use the formula. Does that make sense to everybody? That should be real simple, is because you're mainly just doing some arithmetic. Okay, now we can also deal with, trig functions and all kinds of things. So let's go through and work with one with a trig function in it for a few minutes. Okay, so the first one you got is 1 plus the sine of pi times 1 over 2. So that's really going to be 1 plus sine of pi over 2, which we can do that on the unit circle here in a minute. So I'm going to go ahead and just kind of keep filling these things out. So I've got the next one is going to be 1 plus sine of pi times 2, or just 2 pi over 2. 2's crossed out, leaving 1 plus sine of pi, which we can also get from the unit circle. Okay, and we go to the next one, 3. Once you kind of see the pattern, it's pretty easy to get. You got 1 plus sine of now 3 pi over 2, okay, which we can also do. And then the next one is going to be 1 plus the sine of 4 pi over 2, which is really just going to be 1 plus sine of 2 pi, like that. Okay, so now it's just unit circle. And we'll go ahead and just kind of look at each of these things. At pi over 2, you have 0, 1. At pi, you have -1, 0. 3 pi over 2, you've got 0, -1. And at 2 pi, you got 1, 0. So then what you do is just remember the sign is the y value on a unit circle, so we want to go ahead and get those put together. And then we'll just write out what the results are. So this one is going to be, when you do this last one, the first one, you're going to have 1 plus 1. So that first term in that sequence is going to be 2. Okay, sine of pi is 0. So you're going to have 1 plus 0. Second term in the sequence is 1. Then go to 3 pi over 2. You have 1 plus -1. So that's going to 0. Okay. And if you look at this, see, sometimes it's kind of deceiving. It looks like it's going down 1, but it isn't. Okay, because what's going to happen is when you go back to this one, you're going to have 1 plus 0, so it's back to 1. So what's going to happen on this sequence is it's going to kind of alternate between those values over and over again. 2, 1, 0, 1, over and over and over again. It should go through, when you go through this pattern, you're just going to be looking up these values right there over and over again. Okay? Does that make sense? Okay? All right, so that's one thing that you want to be able to do, is to list out terms in a sequence. Now, these are explicit formulas. Now I'm going to go down and let's learn how to do the implicit formulas. You want to be able to generate these as well. Okay, so this is a implicit formula on example 3, whereas the ones we just did were explicit. Okay, and what an implicit formula is, the formula tells you how to get the next term in a sequence. So basically A1 is 32. And if it's an implicit formula, I have to give you the first term, then the formula tells you how to get the second term. So when you go to the next one, what you're really doing is you're doing A of 1 plus 1. Now I'm going to write this out so that you see how the language of this works. N is 1, so we're going to have A sub 1 over 2. So really what you do is you do the previous term and you divide it by 2. So when you do that, you're going to have 32 over 2, so that's going to be 16. So all this implicit formula is doing is it's dividing the term by 16. So what's the next term in your head? 8. Then what? 4, and so forth. Now the way the language goes is like this. The next one you would go a sub 2 plus 1. That's how you get the 3. Well, it's a sub 2 over 2. So it's 16 over 2. So that's equal to 8. Okay, just so that you see how the subscripts work. That's the reason I'm writing all that out, just to help you see how that works. Then the next one would be a sub 3 plus 1. So that's a sub 3 over 2. So that's 8 over 2, which is going to give 4. Okay, so what's going to happen with that sequence is, you know, it's going to go 2, 1, then it's going to start getting into fractions and everything like that. So we will actually start talking about what the limit of this sequence is. So let me just ask you that question. We're not quite there yet. But if it goes 4, 2, 1, 1 half, 1 fourth, 1 eighth, is that sequence going anywhere? Is it heading somewhere? 0, right? Okay, it's heading towards 0. Okay, because what's going to happen is you get way, way out there, you just have 1 over infinity, don't you? So the limit of that sequence, when we start talking about that, is going to be 0. Okay, so we can do a limit of a sequence. Okay, let's go ahead and really start you off with the first couple of terms and then let you finish up 3 and 4. So a1 is 1. That's a given. Okay, when you do the next term, you're really doing a sub 1 plus 1. You follow exactly what it tells you to do. So it's a sub 1 squared minus 1. Okay, so let's see. What you get is a sub 1 is 1. Then you do 1 squared minus 1. So that's equal to 0. Okay, go ahead and do the next two and see what you get. Okay, just want to make sure everybody understands the language and the terminology of how this implicit formula works. So next thing you do is you go to a sub 2 plus 1 and then a sub 3 plus 1. Okay, you just do you do to the previous term, square it and subtract 1. That's what you're really doing. Now you can do this in your head. Okay, what are the next two terms? Okay, yep, okay, so the next one you would have a sub 2 was 0, square it, minus 1. You're always taking the previous term, squaring it minus 1, so that is going to be negative 1 is what you should get there. Okay, go to the next one, you're going to do the previous term, negative 1, square it, minus 1, so that's 1 minus 1, so that gives 0. Okay, now when we start looking at a limit of a sequence on this one, you're going to find that this sequence is going to keep kind of jumping back and forth between numbers, so it isn't going to go anywhere. If you go to infinity, that one's going to do what we call diverge. It's not going to go to any specific value. Okay, all right, now let's go to the next thing here. I want to kind of show you one other type of implicit formula. And see, the way this one is written is I'm really giving you the first two terms. And then I'm giving you a formula that will give you the next term. So this is still an implicit formula. But what it's doing is you're starting with the first two terms. Okay, so, well, let's see. Think basically on this you need to add a blank for a sub 0. So that's a 1, like that. Okay. Then a sub 1 is also 1, so that's how that one's going to start off then. Okay? Now what we need to do when we get to this next thing here, when we do a sub 2, we're really doing a sub 1 plus 1. Okay, in this formula is going to be 1. So what we're going to do is a sub 1 plus a sub 1 minus 1. So what that's going to tell you to do is it's really just telling you to do this. A sub 1 is 1. A sub 0 is 1, so 1 plus 1 is 2. What it's really telling you to do is to add up the previous two terms. Okay, that's how that goes. Then when you go to the next one, a sub 3, what you're really doing is a sub 2 plus 1, right, to get 3. Well, according to the formula, you're doing a sub 2 plus a sub 2 minus 1. So what I'm doing is I'm just replacing the n in that formula with 2 now. Well, let's see, what do you get? You get a sub 2 plus a sub 1. So that would be 2 plus 1, so that's equal to 3. Now, once you see the pattern, you could tell me what comes next. What comes next? 5, exactly. Okay, so what you're doing from here is you're just adding the terms up. So this one will be a sub 3 plus 1. So it's really a sub 3 plus a sub 2. Okay, so that's 5. Okay, does that look like anything that you've seen before? That's the Fibonacci sequence. Okay, so the Fibonacci sequence can be written as in general as a implicit formula like that. But if you do the Fibonacci sequence, you have to start with the first two terms. And you're going like that forever and ever. So you'd have 8 to get the next term and 13 and so forth like that forever and ever and ever. Okay? So here's a picture of Fibonacci and Donald Trump. Why did I put Donald Trump on here? Well, Fibonacci, has all these kind of things on it. Fibonacci was credited for kind of exploring this thing right here. You may have seen stuff like this. So Fibonacci numbers are a part of spirals. So the idea is in your ear, I don't know how accurate this is or if it's different for different people, but it certainly is different for different people, but you can approximate this spiral like going from the beginning of Donald Trump's ear right there and then going all the way around like that. You got this spiral. I've seen that kind of before in the Fibonacci sequence. So I happened to find that on the internet the other day, so I thought that was kind of funny. So there's Donald Trump. All right, so that's a Fibonacci sequence. That's how you can write that thing out. All right, now let's continue with just a little bit more with the explicit formulas. I don't want to do anything on the limits today. We're going to do that on Wednesday. So the idea with this is we're going to try to write some sort of a general formula on this one. Now this is where it gets a little harder. So we're going to try to find the formula on this. Now what you're always doing is you're always looking for a pattern. The pattern on this is not that hard to see. I mean, what's happening to your denominator? It's just doubling each time, right? Okay. So what would be the next two terms? After 1/16, what's next? 1 over 32, 1 over 64, like that. Okay, so that's what it is. The pattern's easy to see on that one. So what we're going to do is we're going to do a recurrence relation, and then what we're going to do is try to write a specific explicit formula on this. Okay, when you do a recurrence relation, you got two things you got to consider. First thing is you just tell me what your first term is. Okay, that's easy enough. That's equal to 1. Then what you got to do is you got to tell me what the next term is in relation to the previous term like this. Okay, so let's kind of think about what's going on. Now, if you look at this problem, we got 1 over 1, 1 over 2, 1 over 4, and so forth. So one thing that we got going on this, without a doubt, is 1 over something, right? We always have a 1 over something. But what's different is we have we have a half, okay? But then what's happening is something basically is changing in there. So what we need to kind of do is think about what did we do to a 1 to make that become, we're doing something to that 1 to make it become a 1/2. Well, what are we doing? We're multiplying it by 1/2, right? Okay, and then that would be how you get that second term. Now that third term, let's see if this still kind of works. We're always going to have a 1 there for that numerator, and what we're doing on this is if we did this, if we took a half, what we're doing on this is now if we multiply that by the previous term, we're trying to get a fourth out of that then. So if you just try like this, See, that's your second term. Your third term gives you that. So what you're doing is you're really doing a half times a half. So let's see if this works out if we just put like an a to the n right there, okay? Or not a to the n, like a sub n, like that. Okay, so if we do this, what we're going to end up having with here is we have a half times a half times a half. We just keep multiplying by a half each time, like this, but you've got some sort of a power going on there. So if we do this, if we put a sub n there, let's see if this will work out then. Okay, let's just see if this will work out. If we do the second term, a sub 1 plus 1, we'd have 1/2 times a sub 1. But a sub 1 is equal to 1, so that would give 1/2, so that would give the second term, right? Okay, if we go to the next term, we would do a sub 2 plus 1. So we would be doing 1/2 times whatever a sub 2 is. A sub 2 is a half, so a half times a half is a fourth. So that's working out. So what we're always doing is we're taking a half of the previous term, okay? And then if you went to the next one, a sub 3 plus 1, well, what are you going to have? You're going to have a half times this previous term, so that's going to be 1/8. So this right here is going to be how you write that occurrence relation. What you have to look at is the way you generate the next term is what do? You multiply by a half, right? So the next one you'd do 1/16 times a half, you would get 1/32 and so forth. So that's how you write the recurrence relation. Okay, does that make sense? And see, once you've come up with something, well, you can tell you're right. You just need to work that out and see if it's giving you what you think. But on the recurrence relation, the idea is, what do you do to the previous term to get the next term? And you should do the same thing over and over again. Okay? Now, let's look at an explicit formula. And let's do this to kind of help us see this. Let's write out 1/1, 1/2, 1/4, 1/8, 1/16. Now, remember, if we're doing an explicit formula, your goal on this problem would be able to find, like, what is a sub 100? What's the 100th term in the sequence? If you just have a recurrence relation, it's too tedious to figure it out that way. So what we want to do is, well, if you look at the pattern on this, the pattern on this is not that hard. You always have a 1 over something, right? But what do you have in the denominator, really? 2, 4, 8, 16. What kind of numbers are those?
2 to the power.
Those are 2 to a power, aren't they? Okay, so this would really be 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and that would really even be 2 to the 0, right? Okay, so that means that when you write your formula for a sub n, it's going to go like that. You'll have 1/2 to what power? Now, the thing that you got to be careful about this is, see, this is the first term, this is the second term, this is the third term. Okay, so how does the exponent relate to the term that you're on? It's 1 less. So you don't say 2 to the n, what do you say? 2 to the n minus 1. Okay, like that. Okay, they're different. Okay, so the idea of, like, if you have your fifth term, they're going to do 2 to the 1/2 to the 4. So this right here would be your explicit formula. It's powers of 2. Does that make sense to everybody? Okay, now what we want to do generally is we want to start n with 1. You could also start it with 0. If you wrote it like this, if you said a sub n equals 1/2 to the n, you would generally want to write this like this. You could write this as n equals 0 to infinity and do it that way too if you wanted to. But generally we're going to try to be consistent and start n with 1. Okay, does that make sense? Okay. All right, let's go ahead. I think we'll go ahead and just stop there then, because it'll take us a little bit of time to do this next one, because it's got an alternating sequence in, and then we'll work on this a little bit more next time then.